Hi guys. So, a limit is a finite value that y approaches as x approaches the same value. We can also have one-sided limits, which is when a limit is evaluated from the right side or the left side. Over here, we have an example of a right and left-sided limit. This limit, as x approaches -7, can be seen at -1 from the left side. This limit, as x approaches -7, is from the right side at -4.
To find continuity, these three things must be true. F of c must be defined, the limit as x approaches c of f of x must exist, and the limit as x approaches c of f of x must equal c. As we take a look at this graph, we should start with the first. F of c is defined. As we look at the graph, f of c is defined at -7 and -4. As we move on, the limit as x approaches c of f of x must exist. Limit as x approaches -7 from the left equals -1. And as we look on the right, the limit as x approaches -7 from the right equals -4. Therefore, the limit does not exist.
Now we're going to look for continuity on this graph. As we can see, there's a point at -7, -1, and the limit as x approaches -7 is equal to -1 from both sides. Therefore, the limit exists, and there's continuity.
As x approaches 1, the limit on the graph of g of x is -3. Oh, wait, but then we need to change. The limit as x approaches 1 on the graph of g of x is -3. So therefore, we use that value to find the point at -3 on the graph of f of x, which is -4. The limit as x approaches 0 on the graph of f of x is 1. And we use that to find the point on the graph of g of x at 1, which is -3. In this limit law, we would take the limit as x approaches -1 on the graph of g, which is -3, and multiply that by -2 to give us a +6, and take the limit as x approaches -1 on the graph of f, which is 3, and therefore we add 3 and 6 to get us 9.
So, limits algebraically is just one method we can use to solve limits, and we're going to work out these three examples. So, the first one is the limit as x approaches 5 for x squared minus 4x plus 3, and all we're going to do is plug in 5. So, we have 5 squared minus 4 times 5 plus 3. And if we solve for that, that's just 25 minus 20 plus 3, which equals 8. And so that means that our answer is 8. For the second one, we're going to do the same thing. We're just going to plug in 5 into x. So it's 5 squared minus 25 over 5 minus 5, which equals 0 over 0. So this limit is undefined. But we can still solve for it because we can see that this top part is factorable. So we're going to factor it, and that'll take away the 0 over 0. So we have the limit as x approaches 5, and we're going to factor that as x minus 5 times x plus 5 all over x minus 5. And then we're going to plug in 5, or once we cancel, then we're going to plug in 5 to what we have left, which is just x plus 5. So it'll just be 5 plus 5 equals 10. So our answer is 10. And then for this one, we can see that in where the equation usually is, there's no x. So for these kind of problems, if you don't have an x in it, then the answer is whatever that is. So the answer is just 304, and it doesn't matter what the limit is approaching. That's it.
If the limit equals 0 over 0 or infinity over infinity, L'Hopital's rule can be used. To do this, you derive the top and the bottom and solve again. In this example, we have the limit as x approaches infinity of x squared minus 1 over 4x squared plus x. When you plug in infinity, you get infinity over infinity. So using L'Hopital's, we derive the top and the bottom, and we plug in again to get one.
Now we will talk about limits at infinity. Limits at infinity evaluate the end behavior of a function as the domain x values either increase or decrease without bounds. Now Jessica is going to work out an example.
So when we're working with limits at infinity, we can disregard insignificant terms. And that basically means that this 5, when we're dealing with infinity, won't make much of a difference. So we can just ignore it and this x. So then we have and then we can simplify a little more and cancel some of these x's. After we can plug in infinity and we find that the bottom is going to be bigger, so our answer is 0.
Insignificant.
When dealing with limits at infinity, a rule to remember is if it's bigger on the bottom or the infinity is on the bottom, your answer is going to be 0. But if your infinity is at the top, your answer does not exist and it's undefined.
When dealing with absolute values, you can never cancel out anything with an x. So, when dealing with limits and absolute values, you can never cancel out anything with an x. These don't have an x, and they're insignificant, so you're just going to cancel them out, and you're left with this. Now we're going to plug in the negative infinity. Okay. The infinities cancel out, and then you're left with 3 over negative 4.